Good afternoon, everybody. Let's start parallel session 8A, particle physics. The first speaker of this session is Sri Rupa Chongdar. Is it correct?
Yes, Sri Rupa Chongdar, yes.
She is talking about the flavored leptogenesis and the type 2 seesaw mechanism with two Higgs triplet scalars. Please share your screen.
Yes. Are my slides visible?
No. Oh, yes. Yeah. We can see your screen.
Okay.
So each talk
yes.
is for 20 minutes. 15 minutes for your talk and 3 minutes for question and comments. So please go ahead.
Yes. Hi, myself Sri Rupa Chongdar, and I will first thank to the organizers for giving me this opportunity. And today I'm going to talk about flavored leptogenesis and type 2 seesaw mechanism with two Higgs triplet scalars. So as the name suggests, I'm going to talk about neutrino mass generation and about flavored leptogenesis. So it is evident from neutrino oscillation phenomena that neutrinos are not massless, rather they have very tiny mass that could not be explained by the standard model of particle physics. So we need a generic mechanism for explaining the mass generation of neutrinos beyond standard model. Seesaw mechanism is such a generic mechanism to explain neutrino mass generation, and here we have chosen seesaw mechanism of type 2, adding two triplet Higgs scalars in the standard model. It is also known that our universe is matter-antimatter asymmetric, and when we say matter, we mean baryonic matter. And baryogenesis is a process by which the baryon number density gets increased over the number density of antibaryons, and some process can generate baryogenesis if the rate of production of baryons and antibaryons differ, satisfying three conditions provided by Andrei Sakharov, commonly known as Sakharov's conditions. Those are baryon number violation, C and CP violation, and departure from thermal equilibrium. So in standard model, there are processes that violate baryon numbers, and C and CP violation also occurs in standard model, but those are not enough to cause the required baryogenesis. So in order to explain the baryogenesis of the new universe, we need new CP violation sources. And seesaw mechanism of type 2, it provides such new CP violation sources by the out of thermal equilibrium decay of the heavy triplet scalars. And it causes leptogenesis. So the leptogenesis gets converted into baryogenesis further by non-perturbative Halleran process. And here we have considered flavored leptogenesis. So it is known that above temperature 10 to the power 12 GeV, the electron, muon, and tau, these leptons are they are out of equilibrium, thermal equilibrium. That is why they all are indistinguishable. So we can consider unflavored regime, but when we go below temperature 10 to the power 9 GeV, these Yucca interaction involving these lepton flavors are all in thermal equilibrium, and that is why they are distinguishable, and we cannot approximate into singly flavored leptogenesis. Also, in case of triplet scalar decays, it interacts with charged bileptons, and those leptons commonly belong to different flavor generation. That is one very important reason why we need to consider flavored leptogenesis in case of triplets. So the motivation of our work is to explain the neutrino mass generation through type 2 seesaw mechanism, and also to estimate baryon asymmetry through flavored triplet leptogenesis. I will first describe the model. Here we have extended the standard model by two triplet scalars, T1 and T2, each with hypercharge 2, and the neutral component of the triplet scalar acquire Wacom expectation values omega 1 and omega 2. And we have chosen omega 1 to be complex here, having a phase alpha. I will be discussing about it later again. And this omega 1 and omega 2, these are constrained by the rho parameter, and they are much less than the standard model Higgs Wacom expectation value V. We have chosen triplet scalars to be of hierarchical masses. Particularly, we have taken T1 to be heavier than triplet T2, so that the lepton number violating effects caused by the decay of T1 can be safely ignored. Also, the lepton asymmetry caused by the decay of T1 can be washed out by the interactions of T2. We have taken the lighter triplet to be of the mass 10 to the power 9 GeV, and here is the extended Lagrangian. It consists of the kinetic term and the Yuka interaction term. So, as I have said earlier, that the triplets undergo Yuka interaction with leptons from different flavor generations, and here is one trilinear term in the scalar potential that breaks the lepton number by 2 unit, and we have chosen the coefficient of the trilinear term mu1 to be complex. Only one triplet scalar is sufficient to generate neutrino mass, but in order to obtain non-vanishing CP asymmetry, we need at least 2 heavy triplet scalars in the model. And so these 2 triplet scalars are going to contribute in the mass generation of the neutrinos. So the each contribution is proportional to the multiplication of the Wacom expectation value of the corresponding triplet scalar and the Yuka coupling matrix. So it is found that the tiny neutrino mass generated is inversely proportional to the heavy triplet mass, and thereby it exhibits the typical seesaw behavior. In the absence of the absolute mass scale of neutrinos, and also it is not yet determined about the Dirac CP and Dirac CP violating angle. So it is convenient and it is customary to introduce zero texture in the lepton mass matrix. In case of Majorana mass matrix, more than 2 zero entries are forbidden, and that is why we have chosen only 2 zero entries in the neutrino mass matrix. So when we add 2 scalar triplets in the standard model, this particular 2 zero texture B2 emerges naturally, considering the horizontal symmetry group Z3. So here the elements E mu and tau tau are made 0, and the parameter space study is shown in this referred paper, and it suggests that this particular 2 zero texture B2 disfavors inverse hierarchy of neutrino mass. The non-zero elements of the neutrino mass matrix can be calculated using this expression shown here. And here U are the U-minus matrix elements, and lambdas are the function of neutrino mass eigenvalues, and the Majorana phases rho and sigma. So using this expression, we can plot and check the allowed parameter space following this particular 2 zero texture B2, and we have plotted the allowed parameter space for these non-zero elements of neutrino mass matrix with the lightest neutrino mass M1, considering normal hierarchy only, because previously I told that the parameter space study shows this texture disfavors inverse hierarchy of neutrino mass. So we have used 1 sigma and 3 sigma data of the latest neutrino mass neutrino oscillation parameters. We have chosen the neutrino mass matrix elements using that parameter space study, and we have kept in mind the upper bound on the sum over neutrino mass. We have kept it below 0.16 eV, and further we will be using these mass matrix elements to calculate the CP asymmetry parameters. Now, to talk about the triplet decay modes, it has two types of decay modes. It can decay into charged pi leptons and it can decay into standard model Higgs. So the interference between the tree level and the one loop decay corrections, we get the CP asymmetry constructed, and to obtain a non-vanishing CP asymmetry, we need at least two heavy triplet scalars. In the one loop decay diagram, we can see there are two types of loops present. The final stage is rather same. It has charged pi leptons, but there are two types of different loops. Here we can see scalar loop mediated by standard model Higgs, and here we can see the lepton loops. And the total CP asymmetry comes from both of these loops. From the scalar loop, we get lepton number violating and flavor violating CP asymmetry, whereas from the lepton loop, we get only flavor violating CP asymmetry. As we considered to study the purely flavored case here, we have chosen the CP asymmetry to be solely composed of the flavor violating CP asymmetry coming from the lepton loop. And that is why we have chosen the tree level branching ratios of the triplet scalars to be in such a way that ensures that one of these two triplets are coupling predominantly to leptons instead of to the standard model Higgs. And we will be carrying out our study taking this condition. The CP asymmetry parameters for each flavor can be calculated using this expression, and when we take sum over all the flavors, we get the CP asymmetry to be vanished because it comes from the flavor violating part. And the CP asymmetry for all flavors, it is proportional to the non-zero mass matrix elements, and it is a function of the triplet Wickham expectation values, standard model Wickham expectation values, and the triplet mass and the phases involved here. So by using all these CP asymmetry parameters, after solving a set of fully flavored Boltzmann equations numerically, we obtain the lepton asymmetries for each flavor generations, and we plot those asymmetries with a factor Z, which is a ratio of triplet mass M and the decreasing temperature of the universe T. And we do the plots for by taking different values of branching ratios. Here we obtain the final saturated value of the lepton asymmetry, and it is also observed from these plots that as long as the purely flavored condition is satisfied, hierarchical branching ratio does not cause any change in the efficiency of the leptogenesis. So finally, we obtain these lepton asymmetries from these plots, and we convert it into the baryon asymmetry using this expression. And here, this A matrix is coming from the chemical equilibrium calculations, and our result, it is, we obtain baryon asymmetry of the order 10 to the power minus 10, which falls within the permissible range of the baryon asymmetry suggested by the experimental studies. Previously, I mentioned that we have chosen one triplet scalar Wickham expectation value to be complex, and the reason behind is here it is, we have seen a phase alpha, which is a CP violating phase, and when we introduce such phase, it helps to it helps to increase the mass difference between doubly charged triplet scalars T1 and T2, and when the mass difference is sufficient, it can kinematically allow a transition, which is very important phenomenologically, and it can give rise to a spectacular signal in the context of LHC. It is already discussed in this paper referred here, and here it is also mentioned that if this phase alpha has a value greater than 65 degrees, then it can be it can show really good mass difference between the doubly charged triplet scalars, and that can lead to a phenomenological special result. So in our work, we have kept this phase alpha greater than 65 degrees. And finally, I want to conclude that our type 2 seesaw mechanism, having two triplet scalars in it, is capable of estimating the baryon asymmetry and the neutrino mass So it creates a breach between the matter-antimatter asymmetry of the universe and the non-zero mass of neutrinos. So future work can be done taking different values of triplet mass that is lower than 10 to the power 9 GeV in order to ensure fully flavored regime. So here I want to finish my presentation. Thank you for watching.
Okay, thank you very much for your talk. It's time for Q&A. Anybody who has a question, please use the shake hands or text the content in the Q&A room. Okay, Bowen, please.
Can you hear me?
Yes, I can hear you.
I'm not quite familiar with the type 2 Seesaw model, but I know in the type 1 Seesaw model, we can generate the Leptogenesis through both the vortex diagram and the wave function diagram. It seems you only consider the wave function diagram. Is there any reason that the vortex diagram doesn't contribute to the Leptogenesis?
Go again, please. I could not understand your question. Can you please go again?
Can you go back to the Feynman diagram of the decay of the
Feynman diagram? Yes. Yes. So we have considered the tree-level decay diagram. From the tree-level decay diagram, the CP asymmetry parameter cannot be constructed. So we need to go for higher loops, and we did not choose vertex calculation here. We only chose the one loop decay diagram, and for simplicity.
I know it's one loop decay diagram. I know in the type 1 Seesaw model, when we consider Leptogenesis, we consider two kind of one loop diagrams. One is this one with a loop in the propagator, and the other one is it's like a triangle loop.
Yes, that is
coming from the
vertex calculation. Yes.
Sorry, I didn't hear.
One comes from the one loop decay diagram, and another is from vertex calculation, wave function and vertex calculation.
Okay.
But here we have only chosen the wave function corrections, so we have one loop decay diagram instead of vertex correction.
Okay.
Okay, any other questions? Okay, if not, thank the Sri Rupa. Now let's move on to the next speaker. Next speaker is Pavel Novikov, who is talking about the lepton mass and mixing patterns from residual modulus matrices. Could you share your screen?
Yes, I hope it's visible now.
Okay, yeah, I can see your screen. Please go ahead.
Great. So I'd like to thank the organizers for this opportunity to present my recent work on lepton mass and mixing patterns from residual modulus symmetries, which was done in collaboration with Joao Penedo and Sergei Petkov. So there will be two parts of my talk. In the first part, I will talk about modulus symmetry approach to flavor in general. I will show that it provides a predictive framework for describing flavor parameters of the standard model. And in the second part, I will concentrate on our recent work and show that hierarchical mass patterns arise naturally within this framework. So let's start with the modulus symmetry approach to flavor. So the ultimate goal is to try to resolve the long-standing flavor problem in particle physics. So we would like to understand in particular why each fundamental fermion of the standard model comes in 3 generations, and why the flavor parameters form the peculiar patterns that we observe. For example, why the masses of different generations are hierarchical, spanning multiple orders of magnitude, and why the neutrino masses are so much smaller than the rest of the fermion masses, and also why the quark mixing matrix is so close to a diagonal one, despite the fact that generically it could be any unitary rotation, and also why the lepton mixing is so different from the quark mixing. Arguably, the most natural approach to this problem is to impose a new symmetry, which is called a flavor symmetry. It commutes with the gauge group, and it mixes different generations, unifying them into multiplets. So modular symmetry is an example of such a symmetry. It is motivated by top-down constructions. It arises in string theories and more generally in theories with extra dimensions. But on the other hand, it can be used from the bottom-up perspective because it allows you to extract predictions without relying on a specific realization within the top-down theory. So let me show you first simplest scenario how modular symmetry may arise in the quantum field theory. So let's assume that we have two extra dimensions compactified to a torus. We can think of them as a two-dimensional plane which repeats itself along two different directions, E1 and E2. And the compactification can be described, its geometry can be described by a complex parameter called the modulus, which is the ratio of these two basis vectors interpreted as complex numbers. So the low energy effective field theory depends on the geometry of the compactification. So in the end, it depends on the value of this modulus tau. Now, the interesting thing is that you can choose a different basis on the same lattice, which will describe the same compactification, but the modulus tau will be different. It is related to the original one via a fractional linear transformation. So it means that the low energy theory should be invariant under such transformations of the modulus. All such transformations form a group, which is called the modular group. And despite its fancy name, it's just a group of 2x2 matrices with integer entries and unit determinants. So it describes all possible changes of basis on this two-dimensional lattice. In your top-down construction, you also have typically some other fields apart from the modulus. And it turns out that these fields transform as multiplets under the modular group, which are weighted, which means that they form a unitary representation rho of the modular symmetry. And they also rescale with a prefactor, which depends on tau and on the constant k, which is the characteristic of a field. It's called the modular weight. And a small technical side note here is that the representation rho is very specific in such constructions. Actually, it's insensitive to most of the modular transformations. So in a sense, it's almost trivial. And in fact, it is effectively a representation of a small quotient of the modular group, which happens to be isomorphic to one of the permutation groups. And this links this approach to a well-known approach with discrete symmetries. In a sense, modular symmetry provides a generalization for this framework. So at this point, we can forget about the top-down realization of modular symmetry, and let's just assume that modular group acts on our low-energy quantum field theory in the following way, in the same way as it is in a top-down construction. And let's assume that this theory is invariant under such transformations. So the next thing we need to do is we need to form singlets, which we can include in the Lagrangian or in the superpotential if we are talking about supersymmetric setting. So for example, if we want to form an interaction of n fields, we write their product and we write some coupling in front of them, which in general can depend on tau. And then from the transformation rule of the product of the fields, we can infer that the coupling in front of them has to transform in a similar way. So it should compensate the weight, the total weight of the fields. And it also has to transform in a unitary representation so that we can extract singlets out of the product of all the participating representations. But y of tau is just a function of tau, just a mathematical object. So we can write explicitly its transformation rule inferred from this interaction. And this means that these couplings have actually to be modular forms because such functions which satisfy this constraint are very well studied in mathematics. They're called modular forms. And what's important for us is that there are only a few of them once you specify the weight. So this space of modular forms is very constrained. And in the end, it means that the couplings will be severely constrained. They will depend on just a small number of known functions, yi of tau, and possibly some coefficients. So if you apply this idea to flavor in the standard model, you assign different generations of the fermion fields, different modular representations and modular weights, and from that you can extract the mass matrices according to the procedure I described in the previous slide. And you get typical expressions like this. So there will be, so the mass matrices will depend on a few functions of tau and some coefficients, and these are the predictions of modular symmetry. So from this you can extract the values of flavor observables, you can feed them and predict the ones which are yet unmeasured. But the issue with these models is typically that if you choose generic values of the parameters, then the resulting observables will be generic as well. For example, you will typically get the electron mass of the same order as the muon mass. And in order to make it much smaller than the muon mass, you have to rely on certain magic cancellations between these coefficients like G1 and G2. So in the end, you don't explain flavor patterns, rather you fine-tune them. And this leads me to the second part of my talk. We tried to address this problem, considering a scenario when flavor patterns arise naturally within modular symmetric setup. So the first thing to notice is that whenever you choose a value of tau, it breaks the modular symmetry completely, because tau is never invariant under fractional linear transformations like this one. However, there exist three values of tau which break the modular group only partially. So they preserve a small subgroup of the modular group. So these values are listed here. For example, if you choose tau to be equal to I, then you have an unbroken Z2 symmetry. And here comes the key idea, because if you have an unbroken symmetry in your theory, it can lead to it can forbid certain terms in the Lagrangian, and in particular, it can make some observables vanish in this limit. And so, for example, if you have the electron mass vanishing in the limit when tau goes to I, it means that if you depart slightly from tau equals I, then the electron mass will become non-zero, but it will be still suppressed with respect to other observables. So this is the key idea, that some flavor observables may vanish as tau goes to a symmetric point. And so in the vicinity of the symmetric point, you can make some observables much smaller than the others. So we used this idea in our work. So what we did is we analyzed the structure of modular invariant mass terms in the vicinity of one of the three symmetric points. So in order to do this, you can write down how the modular invariant mass matrix transforms under a modular group element. It transforms like this in order to compensate the transformation of the fields. So we have an equation of M, and then you can expand both sides in powers of epsilon, which is the deviation from the symmetric point. And from that, you can infer which terms are forbidden for each of the entries of the mass matrix. And in this way, you can derive its hierarchical structure. In particular, it turns out that the algorithm is as follows. You start with you only need to know the representations of the participating fields with respect to the modular group. From that, you can infer the representations under the residual preserved subgroup, which is an abelian group. So they fall apart into singlets. From these singlets, which participate in this equation, you can find the hierarchical structure of the mass matrix. So here there are some coefficients in front of each of the entry, but I only write here the orders of magnitude in epsilon. And from that, you can check whether masses are hierarchical or not. So in this case, they are, but in general, this is not the case. So the first key result is that it is actually possible to build hierarchical masses in this case, which is not obvious from the outset, because if, for example, the electron and the muon mass are suppressed in the symmetric limit, then it could happen that they would be the same order in epsilon. However, it turns out that for specific choices of representations, they will be hierarchical, and you get three masses of different orders in epsilon. And the second result is that we have listed the possible pairs of field representations under the modular group. which realize such hierarchical masses. So we have long tables of all the possibilities in our paper, which is very useful for model building because we can ignore the other choices if we want to have naturally hierarchical masses. So another aspect is large mixing in the symmetric limit, which is what's needed for the leptons. Because typically, if you have a residual symmetry in certain limits, then it constrains your mixing matrix significantly. But in this case, we want to have at least 2 large mixing angles to avoid fine-tuning. So this issue was actually studied in much detail in the context of arbitrary symmetry groups by Riumiaggio and Romanino in their paper. So they found that the form of mixing matrix in the symmetric limit significantly constrains the representations of the participating fields. So to this, we have added 2 more cases relevant in our setup when either the charged lepton masses or all the neutrino masses vanish in the symmetric limit. But the bottom line here is that, once again, the structure of the mixing matrix in the symmetric limit puts certain constraints on the representations of the fields under the modular group. So armed with these 2 sets of constraints on the representations, one coming from the hierarchical masses and another from the large mixing, we were left with a handful of choices. And out of them, we chose the model which is the most predictive in the sense that it has the smallest number of parameters. So it yields certain representations for the fields. Here we assume Seesaw type 1. So we introduce also heavy neutrino triplet. And we study the behavior of the resulting modular invariant model in the vicinity of one of the symmetric points. So as you can see, when you do the explicit calculation in this model, you get a charged lepton mass matrix, which is hierarchical. So some of its entries are suppressed with different powers of epsilon, and it reproduces the hierarchical masses of charged leptons. So they are of different orders in epsilon. Now, the nice features of this model is that all of its parameters are order 1, and each of them can be varied in a broad range without significantly affecting the observables. So in this sense, it is free from fine-tunings. It also reproduces the charged leptons, as I have already said. Apart from that, it fits the known lepton flavor observables, like the mixing angles and the mass square differences of neutrinos. And finally, it makes certain predictions about the observables which are yet unmeasured. In particular, it predicts the smallest neutrino mass to be 0, which means that the sum of masses of neutrinos is roughly 0.059 eV. It also predicts the CP violating phase delta in the lepton sector to be very close to a CP conserving value of pi. And finally, it predicts the effective Majorana mass to be roughly 1.44 millielectron volts. But I'd like to stress that this model, of course, is not the key result here, because this is not the end of the story. One could imagine many generalizations, or one could try some other models as well. And the key point, it turns out to be possible to explain the hierarchical masses naturally within this framework, which was not done before. And this leads me to my conclusions. So we have seen that modular symmetry provides a predictive framework for describing flavor parameters. In particular, I have shown you that the resulting mass matrices depend on just a small number of parameters. One of them is the modulus tau, and there are also sub-coefficients. And secondly, we have seen that hierarchical mass patterns arise naturally within this framework if you choose the value of the modulus tau close to a symmetric value. So I will stop here. Thank you for attention.
Okay, thank you for nice talk. We have a few minutes for Q&A. Anybody who has a question, please click on shaking hands or use Q&A room. I have a short question. Is it possible to accommodate quark mass patterns by using this symmetry?
Yes, that's for sure. I think it's a very straightforward generalization. In a sense, it might be even easier than for leptons, because in the case of quarks, you don't have this severe constraint from the mixing, because typically what you get in the symmetric limit is that the mixing matrix is constrained and all of the mixing angles become zeros. So this is not a problem for quarks. And so I think that there will be more possibilities for quarks. Otherwise, the procedure is analogous for quarks, I think.
Okay, thank you. Any other questions? If not, let's move to the next speaker. Thank you for a nice talk.
Thank you.
Okay. Next speaker is Deborah Barreiros, talking about neutrino masses from simple Scotto Seesaw model with a spontaneous CP violation. Deborah, please. Okay, yeah, you share the screen. Please go ahead.
Okay, thank you. Hi, everyone. First of all, I would like to thank the organizers for the opportunity to present my work here at PASCOS. My name is Deborah Barreiros, and I'm a PhD student at CFTP Lisbon. And today I will show you the work I've done in collaboration with Philippe Joaquim, Raul Srivastava, and José Valle about a very simple Scotto Seesaw model where CP violation arises spontaneously. Well, as you all know, the standard model cannot explain the existence of neutrino masses and lepton mixing, and also doesn't give us a suitable dark matter candidate. So one must go beyond the standard model to try and solve these two problems. And one can do that, for instance, by considering type 1 seesaw mechanism, where neutrino masses are generated via the exchange of very heavy right-handed neutrinos. But if we want to consider as well dark matter, then we may as well look at some kind of scottogenic model where neutrino masses are generated via the exchange of some dark particles at the radiative level. Well, in the case of this particular work, what we did was to consider a model where both mechanisms contribute to neutrino masses, and we added as well a single discrete symmetry in order to be able to accommodate neutrino oscillation data, dark matter stability, and also spontaneous CP violation. But the starting point for this work is a model that was proposed back in 2019 by Valle and collaborators. And what they did in this work was to associate the two different mass scales that are measured in oscillation experiments with two very different mass generation mechanisms. In the most simple case, where the lightest neutrino is massless, then the atmospheric mass scale may arise at tree level from the type 1 seesaw mechanism, while the solar mass scale can emerge radiatively through a scottogenic loop. This is why they call this mechanism the Scotto Seesaw mechanism. And they did this by introducing a standard, singlet, a right-handed neutrino to the standard model, along with other two dark particles, a scalar doublet, along with a fermion singlet F. And both these particles are oddly charged under dark Z2. And because of that, we have the following allowed diagrams for neutrino masses. And as you can see, the exchange of right-handed neutrinos at tree level will generate the atmospheric neutrino mass scale, while the radiative exchange of eta and F, our dark particles, will generate the solar neutrino mass scale. So at the end, when we look at the effective neutrino mass matrix, we can see the contribution of both these mechanisms. So as you can see, this is a very simple model, and it predicts one massless neutrino, can accommodate without any kind of problem neutrino oscillation and LFE data, and provides a viable WIMP dark matter candidate. However, if we do not constrain somehow this Lagrangian, then we will not get any predictions for low energy observables. So what we did to solve that problem was to require the Lagrangian to be CP symmetric, and because of that, we had to find an alternative source for CP violation. And we did that by introducing a new scalar singlet sigma with a complex wave. And these are the couplings that are allowed in this case. As you can see, we have couplings of sigma to our neutral fermions, which after spontaneous symmetry breaking give origin to Majorana mass terms for these fermions with complex couplings. So as you can see at the effective level, we end up with a phase that cannot be taken away. So in principle, CP violation can be transmitted to the neutrino sector, provided of course that this phase here is non-trivial and that our neutral fermions couple differently to sigma and sigma conjugate. Also, one must ensure as well that our scalar potential contains this phase sensitive term here, sigma to the fourth, as I will show you later on in this presentation. So as you can see, once we have this scalar singlet sigma to the minimal Scotto seesaw model, we then have a template for neutrino masses, dark matter, and spontaneous CP violation. However, if we don't constrain somehow even further the number of parameters at higher energies in our model, we will still end up with no predictions for low energy observables. So what we did to solve, once again, that problem was to try to forbid some of the couplings by using some kind of discrete flavor symmetry. Well, in the most simple case where we only have one right-hand neutrino and one dark fermion F in the model, any discrete symmetry that we use to try to forbid some of the couplings will immediately lead to incompatibility with neutrino oscillation data, either because we get one of the mixing angles, the Lepton mixing angles to be 0, or because we get one extra massless neutrino. So, in order to solve that problem, we added an extra right-handed neutrino, as you can see here, new R2. And the most minimal discrete symmetry that we found that led to maximal constraints was this Z8 symmetry here. Of course, that this is not the only possible charge assignment that we can have for our fields. We could also interchange the charges of our Lepton doublets, and that would lead to other two possible charge assignments, which here we name Z8 E mu and Z8 mu tau. Okay, so taking this table into account, these are the contributions to neutrino masses at tree level, and we got these contributions at loop level. Notice here that we had to add an extra waveless scalar singlet in order to be able to close the scottogenic loop. Okay, and these are our allowed Yukawa and mass matrices. So as you can see, our goal was met because we indeed forbid some, we were able to forbid some of the couplings. And also notice as well that our charged lepton sector is non-diagonal. In fact, we have a mixing between two of the three flavors, between the electron and the tau flavor for the specific case of this symmetry. This is actually why we call this symmetry Z8E tau. And we also end up with a decoupled muon. Okay, so moving on to the scalar sector, this is our scalar potential. And as you can see here, once we minimize it, we get this CP violating solution, which will correspond to the global minimum as long as this condition here is fulfilled. Also, notice that we get indeed a non-zero vacuum phase at the potential global minimum, as long as this term here is present in the potential. Okay, other conclusions that we may take from this potential is that our Z8 symmetry is broken down to a remnant Z2 symmetry, which will stabilize dark matter. And why is that? So because our neutral dark scalars will not mix with the non-neutral dark scalars, and we will end up with two possible dark matter candidates, either our dark fermion F or the lightest of the mass eigenstates from the mixing between eta and chi. Moving on to the low energy constraints, recall that these were the matrices that were allowed by our symmetry Z8. And once we put this information in the effective neutrino mass matrix, this is what we get. So as you can see, our symmetry imposes a 0, which we can test against neutrino data. And also notice as well that the contribution from the scottogenic loop is really crucial in order to ensure the existence of CP violation. If these terms were not here, then this phase could be taken away and CP would be conserved. Okay, so once we go to the bases where charged leptons are diagonal by rotating this matrix using the charged lepton mixing matrix, we will end up with 3 possible constraints depending on our charge assignment for decoupled electron, muon, and tau. And we can test these constraints against neutrino data. And for that, we use this global fit of neutrino oscillation data from the Valencia group. And in fact, our condition corresponds to two low energy constraints because this corresponds to a complex matrix. And once we test those low energy relationships, we get these results. Here I show you the results in the plane of theta to 3 delta for our three possible cases of decoupled electron mu1 and tau, and also for the two possible neutrino mass orderings, normal ordering and inverted ordering. Notice that I don't present here the case of inverted ordering and decoupled electron because it is automatically excluded since it leads to vanishing neutrino-less double beta decay. And we know that that is incompatible with inverted ordering. On the other cases, I here present the allowed regions at 1 sigma, 2 sigma, and 3 sigma. And for comparison, I present here as well the contours from the global fit. And for these three cases, as you can see, the model allowed regions coincide with the experimental ones, while for the case of normal ordering and decoupled mu1, the model selects the first octant for theta to 3, and for the case of normal ordering decoupled tau, the model will select the second octant for theta to 3. So as you can see, once we get a better measurement of this angle, we will be able to exclude either one of these cases. Now moving on to constraints on the lightest neutrino mass, I here present the results in the plane of m lightest delta. And as you can see, for the case of normal ordering and decoupled electron, our model establishes both an upper and lower limit for m lightest. And both of these limits are still well below the current limits from cosmology and Catherine. But the same doesn't happen for these three cases here, where you can see that our model establishes a lower limit for the lightest neutrino mass, which is now being currently probed by cosmology. Finally, for the case of inverted ordering and decoupled mu1, you can see that our model still is still compatible for smaller masses, smaller lightest neutrino masses. And we indeed have compatibility for at 1 sigma, 2 sigma, and 3 sigma. Now, regarding the constraints on neutrino-less double beta decay, the interesting thing of this model is that even though we are considering a very simple discrete symmetry, a Z8 symmetry, we still get some lower limits on m beta beta for normal ordering. In fact, our model establishes a very small compatibility region for normal ordering and decoupled mu1, normal ordering and decoupled tau. And these regions are almost entirely excluded by current limits on m beta beta. And certainly future updates on these experiments will be able to probe the entirety of the regions. For the case of normal ordering and decoupled electron, we still have some, this case is still compatible because of course it predicts m beta beta equal to 0, which is still allowed by neutrino oscillation data and m beta beta current experimental limits. Regarding inverted ordering, we still have to wait a little bit longer for next generation experiments in order to be able to probe the entirety of the regions. So to conclude, we proposed a very simple Scott-Seesaw model where neutrino masses, lepton flavor structure, dark matter stability, and also spontaneous CP violation are accommodated with a single Z8 flavor symmetry. This symmetry is then broken down to a dark Z2 by the VEV of a new complex scalar singlet. This remnant Z2 also stabilizes dark matter. And the complex VEV of these scalar singlet will be the unique source of CP violation, and it will be successfully transmitted to the leptonic sector via the couplings of sigma to our neutral fermions. And also this Z8 symmetry will also be responsible for low energy constraints, which we tested against neutrino data. And we concluded that for normal ordering, the predicted ranges on M lightest will be fully tested by near future neutrino-less double beta decay experiments, While for inverted ordering, we still have to wait a little bit longer for a better determination of the Dirac phase and also for further improvement in sensitivities of upcoming neutrino less stable beta decay experiments. Well, thank you very much for listening to my talk, and I'm happy to answer to any questions that you may have.
Thank you for interesting talk. It's time for Q&A. Anybody who would like to ask, please click on the shaking hand. Okay, Bowen, please.
Hi, maybe I've missed what is the mass scale of the vacuum expression value of sigma?
Well, it is not. We don't impose any limit on the VEV of sigma. It can be whatever.
So it can be very small, like GeV scale.
Yeah.
Or even MEV scale. Okay.
Yeah.
Okay. So the Z8 symmetry is only broken by this the vacuum expression value of this sigma. It's not broken by the vacuum expression value of standard model Higgs.
No, it's broken by the VEV of sigma. Yes. Yes. Yes.
Okay. Okay. So, thank you.
So any other question? I have a quick question. Can you briefly comment on how leptogenesis can be realized in your model?
Well, we have two right-handed neutrinos.
Yes.
So in principle, we can have some kind of leptogenesis going on. Well, I guess it will depend as well if our constraints will allow for leptogenesis, because they will for sure constrain DCP asymmetries, because we have a relationship between delta and theta to 3, for instance, and also other relationship because we have to from this condition here. So I guess we would have to make the calculations in order to be sure if it would work.
In that case, do you think that the new CP source you introduced can play an important role in achieving Lepton asymmetry?
Yeah, it can have an important role, yes, because since we have these constraints, then the Yukawa couplings that appear in DCP asymmetries will depend on the Dirac phase, and because our Dirac phase is constrained, then yes, it can influence that.
Mm-hmm. Okay, thank you. Any other questions? If not, let's move to the next speaker. Thank you, Deborah. Next speaker is the final speaker, Bowen Fu, is talking about dark matter in the type 1B Seesaw model. Can you share your screen, Bowen?
Yeah, sure. Let me share my screen. Okay. Okay.
Okay, I can see you.
Correct screen, right?
Okay, please go ahead.
Okay. Hello, everyone. I'm Bowen from the University of Southampton, and the title of my talk is Dark Matter in the Type 1B Seesaw model, as advertised. And this is based on our previous work in February, together with Marco and Steve. So first, I want to talk about the dark matter production. In general, there are two different mechanisms for dark matter production. The first one is called freeze-out, which assumes the dark matter is in equilibrium after the reheating, and the universe cools. As the universe cools, it decouples from the thermal bars, and the common density freezes. The other one is called freeze-in, which assumes the dark matter has a neglectable common density at the end of reheating, and it is produced from the thermal bars before it decouples as the universe cools down. In any case, the final radical abundance should meet the observed one, which is measured by the Planck collaboration. This gives one of the constraints to our result. And in this talk, we will assume the dark matter is produced through the freezing mechanism. Then I want to talk, and I want to make a general discussion about the neutrino portal. What I mean by neutrino portal is basically this term. There are 3 particles in this portal: a dark scalar phi, a dark fermion chi, and a right-hand neutrino. And in the so-called heavy scalar scenario, we have the dark scalar, the heaviest one, and it can decay into a dark fermion and a dark scalar, and a right-hand neutrino. Where the dark fermion is stable and plays the role of dark matter candidate. So under this framework, the dark matter can be produced through 3 diagrams. The first one is a scattering between standard model leptons and standard model Higgs, mediated by a right-hand neutrino into a dark fermion and a dark scalar. We call this process the neutrino cover process. And the amplitude of this process is proportional to capital Y square times small y square, where capital Y is the neutrino cover coupling, the Seesaw cover coupling, and the small y is the portal coupling. And the other 2 processes are called dark sector process. They are the scattering between 2 right-hand neutrino into 2 dark scalar or 2 dark fermion. And the amplitude of this process are proportional to small y to the power 4. So as we are interested in the connection between neutrino physics and dark matter, we are more interested in the first diagram, the neutrino cover process, as the dark sector process are totally determined by the portal coupling. Then you may ask why we want to use type 1b Seesaw model instead of the traditional type 1c Seesaw model, which we call it type 1a Seesaw model. Here is a comparison of the 2 different models. In the type 1a Seesaw model, the neutrino mass is generated by 1 Higgs doublet. And to have a GeV scale heavy neutrino, the Seesaw Yukawa coupling has to be roughly of order 10 to the minus 7. And in that case, the coupling is too small to have a neutrino Yukawa process dominating the dark matter production. There have been some research about this, and it can be shown that in the little Seesaw model, type 1 Seesaw model, the neutrino mass have to be larger than 4 TeV in order to have the neutrino cover dominance. However, in type 1b Seesaw model, the neutrino mass is generated by the symmetry breaking of 2 different Higgs doublets, and there are 2 different Yukawa couplings. Then we can make one of the coupling to be very small, the other one to be can be relatively large. And in that case, the large coupling can play a role in dark matter production. Then let's look at our model. The particles and their symmetries are shown in this table. Besides the standard model fermions, there are 2 Higgs doublets, 2 right-hand neutrinos, and 2 dark particles, phi and chi. In addition to the standard model SU2 cross U1 symmetry, there is a Z3 symmetry and a Z2 symmetry. The Z3 symmetry is used to ensure the standard model fermion mass is generated through type 2 Higgs doublet model. And the Z2 symmetry ensures the dark fermion is stable, which makes it a dark matter candidate. And the Seesaw Lagrangian neutrino portal are like this. We have two right-hand neutrinos coupling to 2 different Higgs doublets, and also dark fermions with different chirality. This is required by the Z3 symmetry. And these 2 right-hand neutrinos can form a Dirac pair as their mass term is like this. They cannot have normal marginalized because of the Z3 symmetry. Then let's look at the constraints. We have a lot of free parameters in the model, so we need some constraints to constrain the parameters. The first one is we consider is the oscillation data. So with the oscillation data, the Yukawa coupling in the type 1b Seesaw model can be reduced to overall factors, namely y1 alpha to y1 and y2 alpha to y2. And the overall factors satisfy this equation. And the next one we consider is the mu and decay. The constraint from mu and decay in type 1b Seesaw model takes this form. And the next one is from collected data. So as widely discussed in the literature, the strength of collected of the neutrino mixing is active stellar neutrino mixing is characterized by this quantity U alpha square, where U alpha is the unitary matrix diagonalizing the total mass matrix of active and stellar neutrinos. And in the type 1b Seesaw model, we have the expression of U alpha square like this, where A and B are some coefficients determined by the oscillation data. And delta M is is a relative Majorana phase. And using the equation from the relation of the couplings from the oscillation data, we can derive a lower limit to the U alpha squares, which depends on the red-handed neutrino mice. Okay, then let's look at our result. The first result I want to show is the required port coupling for the correct radical abundance. In these figures, we set the tangent beta, which is defined by the ratio of two vector expression values in the two Higgs diplet model. We set it to be 10. From left to right, the heavy neutrino mice change from 1 GeV to 10 to the power 2 GeV to 10 to the power 4 GeV. And you can notice the vertical axis is the ratio of the dark particle mices. It can be proved that if the dark scalar is much heavier than the other particles in the neutrino portal, the dark matter production only depends on the ratio of dark matter masses instead of individual dark matter mass. And in different scenario for dark sector dominance, the portal coupling follows this expression, and in the neutrino cover dominance scenario, the Yukawa coupling takes this expression. This is from solving the Boltzmann equations. And if you look at the figures, you can find some yellow lines in the figures. Above those yellow lines, the dark sector process are dominating the dark matter production. And below, the dark matter production is dominated by neutrino cover process. And you can see in the first figure, there is only a very small region allowed for neutrino cover dominance because of the collider limit. And as the neutrino mice increases, the allowed parameter space for neutrino cover dominance is increasing. And on the right, the figure on the right, you can find in the figure on the right, you can find some lower limit for the dark sector dominance. This can also be derived analytically. And if you go for some larger neutrino mice like 10 to the power 6 GeV in most of the parameter space, the neutrino cover dominance will be favored. Then I want to show the experimental constraints more explicitly. In these figures, the shadow area are excluded for different reasons by different constraints. And we also marked out the sensitivity of future experiment SHIP and FCCE, which are the red and the orange lines. And the ratio of dark particle masses is fixed to be limit, which is 1. You can find some color dashed lines in the figures, a green one, a blue one, and a purple one. Above those lines, the dark matter production is allowed to be dominated by neutrino Kawa process. And below those lines, the dark matter production is definitely dominated by the dark sector process for the corresponding conditions. And when the tangent beta increase from 10 to 30 to 60, you can find the lines move downwards, which means the parameter space is less constrained. And among these three figures, the strongest constraint is from the muon neutrino mixing. Besides tangent beta, we can also change the dark particle mass ratio. So in these figures, we fix tangent beta to be 10 and change the mass ratio from 1 to 10 to the power 4 to 10 to the power 8. As you can see, this time the dashed line moves upward as the mass ratio increase, which means the parameter space is more constrained. And again, the strongest constraint is given by the muon neutrino mixing in the middle. So in summary, we have discussed the dark matter production in a realistic model with a neutrino portal, which is the minimal extension of type 1b Seesaw model. And we have seen that the dark matter neutrino relation can be constrained by the current experimental result, and when the heavy neutrino mass is GeV scale. And the result can be further constrained by future experiment like SHIP and FCCE. For future work, we found that the type 1b Seesaw model can be realized effectively in some more complicated model to include the leptogenesis. And hopefully we will have another paper coming out next week. Thank you for listening.
Okay, thank you for interesting talk. It's time for Q&A. Anybody who would like to ask, please click on shaking hand. So I have a question. You introduced two heavy neutrino, singlet neutrino, N1 and N2.
Yeah.
Is it possible to impose either of heavy neutrino to be KV massive particle?
In that case, I think in that case you will need the. I'm not quite sure, because if you have some KV scale neutrino, if you have some KV scale heavy neutrino, the
So it seems that you assume that the Mn to be order of GeV. How about the others? They are you suppose they are the same, or the other?
We have one neutrino mass. We don't have one neutrino mass because the neutrino mass is actually Dirac. The two.
Dirac. Nice.
Yeah, the two right-hand neutrino, we call it right-hand neutrino, but they can form a Dirac pair, like I said. The majority mass is forbidden by the J3 symmetry. So yeah, there is only one mass in this model.
Okay, yeah. But if you abandon the symmetry like G3 or G2, then still it is possible to impose lepton number violating terms for neutrino mass. Is it right? In that case, it seems that your models become similar to the so-called inverse Seesaw model, I think.
Yeah, it's actually quite different from the inverse Seesaw model. It's more like but yes, if you abound the J3 symmetry, we can have some we can have some symmetry breaking, CP breaking term, the Lepton number breaking term. But the purpose of our research is to have this type 1B Seesaw model. If we have some like you said, if we have the Lepton number breaking term, the Majorana mass of the ratic neutrino, there will be no difference between this model and the type 1A Seesaw model. The neutrino mass can still be generated through this way. And in that case, we have to make the coupling to be small to meet the to get the correct standard model neutrino mass. So in that case, we cannot make the coupling large, and we will lose the connection between dark matter and the neutrino physics at GeV scale.
Okay, so any other questions? If not, thank Bowen and all the speakers in this session. I think the next session, plenary 6, will be resumed at 5:20. Okay, thank you for all the speakers and the participants. I close this session.